In this video, we are going to prove that script I of g is normal in script A of g, and the script I of g is isomorphic to g mod z, where z is the center of g, and of course, order of an element in a group G is same as order of its image under an automorphism of G. So, of which script I of g isomorphic to g mod z can be asked in section C. So that we will prove at the end. First, we will prove that script I of g is normal in script A of g, and order of A is equal to order of phi of A, where phi is an automorphism of G. So that question from section B is this. Prove that the set of inner automorphisms of a group G, which is script I of G, is normal subgroup of the group of automorphism of G, which is script A of G. So what is given to us, we shall write, let G be a group and script A of G be the collection of all automorphisms of G, and script I of G to be the set of all Tg in script A of G, where G range over capital G. Now we claim that script I of G is normal in script A of G. Now since Te, which is the identity element on G, being an inner automorphism, we have that to be present in script I of G, and therefore script I of G is non-empty. See, our aim is to show that script I of G is normal in script A of G. So that means, first of all, we have to show that the script I of G is non-empty. So that is what is said here, and we have to check the criterion for script I of G to be a subgroup. That needs to be established, and then we have to show, we have to check the normalcy condition. That is, for every element in, suppose I consider T to be an element in script A of G, and I consider an element, say Tg, in script I of G, then T composition Tg composition T inverse belongs to script I of G. So if we can establish these three only, we can say that our script I of G is normal in script A of G. So we have first said that it is non-empty. We know this, that is Tg, how it is defined. It takes an element x to G inverse x G for every x in G. So as said earlier, this Te being a member of I of G, it is non-empty. Now to show that closure and inverse exist, we first prove this result. That is, if you consider Tg and Th in script I of G, then its their composition is nothing but T suffix Gh. So this is what we are going to establish first, and that will let us that this group, and that is this script I of G, is a group. And then we can even use this to show that for any Tg, its inverse also exists. The same result can be used to prove that also. And then normalcy condition will establish. So to prove that these two mappings are equal, when their images are equal. So we consider the image of x under Tg composition Th. Where is that x? X is any arbitrary member of capital G. X is any arbitrary element. So this is true for every x. Whatever discussion that we have here, it's true for every x in G. Now x Tg composition Th, by the definition of composition of mapping, this is how we write, and by the definition of Tg here, we write x Tg as this, G inverse xg. Under Th, this element will be taken to H inverse G inverse xg H, and that on simplification gives us that this is nothing but Gh the whole inverse. The reason is known to us, that is AB the whole inverse is B inverse, AB the whole inverse is B inverse A inverse. This is known to us. So using that only we have this, and this obviously tells us that this is nothing but the image of x under Tgh. So as the images are equal, the mappings must be equal. That is, Tg composition Th must be equal to Tgh. So this will help us in proving the closure as well as inverse. So we have considered Tg and Th to be any two members of script IFG. For any element to be in script IFG, you just see the description of this. We have the suffix to be a member of capital G. When you have G and H, when you have G and H to be members of capital G, GH is also a member. And proving that this being a homomorphism, this being a homomorphism, composition of a homomorphism is again a homomorphism, and 1-to-1 on 2 will imply the composition is also 1-to-1 and on 2. So we have this to be an inner automorphism, and therefore closure holds in script IFG. Now as for inverse is concerned, in this we notice that Tg composition, Tg inverse is Tgg inverse because of this, which is identity, and in the same way you have this also to be true, Tg inverse. So that in turn implies that T suffix G inverse is nothing but the inverse of Tg. So here why we get this is, we know that A dot B equals C equals B dot AE is identity element. Then whatever here I have will be the inverse of this, and this is how we denote it. So we have this. So G inverse belongs to G. We know whenever G belongs to capital G, therefore Tg inverse should belong to this. So for any Tg in script IFG, Tg inverse is also in script IFG, and therefore script IFG is a subgroup of script AFG. Now to prove that script IFG is normal in A of G, script A of G, normal in script A of G, we shall consider an element, say T in A of G, script A of G, and Tg in this. Our job is to show that, see, we know the definition of normal subgroup. We have N is normal in G. N is normal in G if for every G in G and N in N, G and G inverse belongs to N. This is the condition. So here in the place of G you have script A of G, and in the place of N you have script I of G. And from here an element considered is T, from here an element considered is Tg. So naturally what we need to check is T composition, Tg composition, T inverse belongs to script I of G. This is what we are trying to establish. So for that we will establish that this is nothing but this. So once I have the proof of this one to be T suffix GT inverse, the image of G and T inverse. If you are able to prove this, then this being a member of script IFG, what is required can be achieved. So we consider, so again this is a mapping and this is also a mapping. To show that two mappings are equal, we have to show that the corresponding images are equal. So for that we shall take an element, arbitrary element, say X in G. Arbitrary element X in G. Then X, T composition, Tg composition, T inverse. By the definition of composition of mappings, this is nothing but Xt under, we have to consider the image of Xt under Tg and the image of this under T inverse. So if you consider Tg, this is how it is defined. G inverse, the element whatever here I have, that should come in the middle, and G as such. And T inverse being a homomorphism. See, this is by the definition of Tg you have this step, by the definition of Tg. And this is by the definition of composition of mappings. And this is because T inverse is a homomorphism. T inverse is a homomorphism because script A of G is a group. So T inverse exists as a homomorphism. So we have this to be G inverse, T inverse, X. We have this to be G T inverse. See here T inverse gives us identity mapping. So you have actually identity mapping you will have, but Xi is X. So that is why it is not written. So now here we are going to rewrite this as GT inverse the whole inverse. And these remain as such. We will establish this. Why is that G inverse, that is the image of G inverse, and T inverse is nothing but the inverse of the image of G under T inverse. That will be established. So presuming that that is established, we have this, and this obviously gives us the image of X under GT inverse. So this is the reason we consider, to prove that, we consider GT inverse composition G inverse T inverse. Because T inverse is a homomorphism, we have this step, and GG inverse being E, you have this, and T inverse being a homomorphism, it takes identity element to identity element. So in the same way, we can show that G inverse T inverse composition GT inverse is E. So again, on the same principle, whenever we have A dot B equal to E, the E is identity element, B dot A, whatever here we have will be the inverse of whatever we have here. So in this case, whatever here we have will be the inverse of whatever here we have. So GT inverse, the whole inverse. So that is what is written here. Thus T composition TG composition T inverse is T suffix GT inverse, and this obviously is a member of script I of G for this reason. T inverse is a mapping from G to G, G belongs to capital G, therefore GT inverse belongs to G. So whatever here in the suffix that we have, that should be a member of capital G. That is how your script I of G is defined. So you have this belonging to script I of G. So all the conditions for script I of G to be normal in script I of G being true, we conclude that script I of G, the group of all inner automorphisms, is normal in script A of G. So in the next one, we will prove that order of an element in a group G is same as order of its image under an automorphism of G. So if G is a group and phi an automorphism of G, and if A belongs to G is of order of A, then the orders of both of them are the same. Now we'll consider A to be what is given as to be written first. Let G be a group and A be a member of G. Now without telling what is happening, where these are all happening, then the proof will be meaningless. So we have to mention that where everything takes place. So all of them take place in first of all in the group G, because once you have an element from G only, the rest of the things can be described. So we'll have to first say that let G be the given group, or let G be a group and A be a member of that. And let us take order of A to be, say, some n, positive integer n. Then by the definition of order of an element, it is the least positive integer, such that A power n is the identity element in G. So n is the least positive integer. We shall name this statement as statement P, and this as equation 1. Now let phi from G to G be an automorphism. Now consider phi of A power n. Now because phi is a homomorphism, we have this to be phi of A power n. But by 1, A power n is E. And because phi is a homomorphism, it takes identity element to identity element. So this is what we get. Phi of A raised to n as the identity element. Now, if we have this to be the least positive integer, then what is required that we will get at once. Now, we do not know whether there will be any other k which is less than n which satisfies this. So, to rule out that possibility, we suppose, if possible, that there is some k less than n for which phi of A power k is identity element. And again, because phi is a homomorphism, we can rewrite this as phi of A power k equal to phi of E. Why this phi of E? Because this E can be rewritten as phi of E, as phi is a homomorphism. This is also because of homomorphism. Phi is a homomorphism, and this is also because phi is a homomorphism. Now from here we get A power k to be E, because phi is 1 to 1. Phi is an automorphism, therefore we have to have phi to be 1 to 1. So this is because phi is 1 to 1. This part already we have said in one of the section B problems that phi of a square, when we consider it is phi of a into a, phi is a homomorphism, so it is phi of a into phi of a, so you have this to be phi of a the whole square. So the same explanation for 2 that is true, and similarly we can establish for k also. So this step is just because phi is a homomorphism. This step is also because phi is a homomorphism. And this step is because your phi is 1 to 1. So, but a par k is less than, a par k is e with k less than n. That's our assumption here. So that's a contradiction to statement P, because we have said that n is the least positive integer for which a par n equal to e. That is, you cannot find any number which is less than n which can satisfy this equation. So we have to have this k to be not less than n. So we have this phi of a par n to be e with n to be the least positive integer. So we have order of a to be n already known. Now that order of phi of a is also n. So we conclude from this that order of the image of a under an automorphism is same as order of that element a. Now in section C, this question can be asked, which states that, the statement of the problem is prove that script I of G is isomorphic to G mod Z, where script I of G is the group of inner automorphisms of G, and Z is the center of G. Now, again, I said earlier, we'll have to write what is given to us. First, let G be the given group. Let G be the given group, and we'll have to mention what are all that we have here. So we'll have to mention let Z be the center, which is all those elements which commute with all the elements of G for every G in G. So that is our Z, and of course script I of G should also be mentioned. It is all those Tg in script A of G where G range over capital G. So what are all given in the statement, we have to tell about them. G, it's a group, and Z comes, so what is it, and script I of G, what is it. So all these are to be mentioned, and then only we should go to the proof of the given problem or given statement. So now we define, say our job is to show that G mod Z is isomorphic to script I of G. So we are going to make use of our first isomorphism theorem or fundamental theorem on homomorphism. So if we can prove that from G to script I of G, we have an onto homomorphism with kernel Z, then by first isomorphism theorem, we can have G mod Z to be isomorphic to script I of G. So that is the idea. So for that, we'll consider a mapping, say sigma from G to script I of G defined in this way. Any element is taken here as small g. So this is defined for every G in G. We can easily prove that this sigma is well defined onto is very obvious. And then it's a homomorphism. So all that can be easily proved. So we can also see that we have, for well defined, we'll have to consider two elements in the domain to be the same. Say G equals G prime. Then this would imply that Gx is equal to G prime x. We want to have G inverse, okay? So G inverse we'll consider. See, our job is to show that here we will write what is required, and then we'll establish it. So we want to show that Tg equals Tg prime. So to show this Tg equals Tg prime, we'll have to prove that their images are equal. So if you consider LHS, it is nothing but G inverse Xg. But G being equal to G prime, it will be G prime inverse Xg prime. But this is nothing but Xtg prime, the image of X under Tg prime. So as the images are equal, the mappings are equal, and therefore we have sigma of G to be equal to sigma of G prime. So you have your sigma to be well defined, and onto is very obvious. And for homomorphism, we can use this sigma of Gg prime. When we consider, it will be Tgg prime, which is nothing but Tg composition Tg prime, and this is nothing but sigma of G composition sigma of G prime. So Tgg prime being written as Tg composition Tg prime, we have established in proving that script I of G is normal in script A of G. So the same technique. So we are just borrowing that explanation here, and then we can have it here easily. Or if, because it is asked for section C, that needs to be established actually. This part is to be proved because it is asked for 10 marks, means that the explanation should also be given. Now kernel sigma, see, we have got this to be well defined on to homomorphism. So once you have your sigma to be homomorphism, you can talk about kernel. So kernel sigma is all those elements in the domain whose image under sigma is the identity element in script A of G, that is taken as TA. So but sigma of G is Tg. So you have this to be equal to all those G in G for which Tg equals Ta. But a mappings being equal implies that the images are equal for every X in G. And so again, this is nothing but the set of all G in G such that G inverse Xg equals X for every X in G. And this is nothing but we can pre-multiply both sides by G. So you have this Xg equals Gx for every X in G. So it is all those elements which commute with all the elements of G. That is nothing but center of G. By the definition of center, it is nothing but center of G. So if we denote that center of G as just Z, then this is what we get. Since sigma from G to script I of G is an onto homomorphism with kernel Z, by first isomorphism theorem, we have G mod Z to be isomorphic to script I of G. So that proves the main part of the theorem. Thank you.